various solutions for using it. And then we'll go into how to actually debug multi-threaded programs. We'll debug two different kind of things, the race conditions and the deadlocks. And then we'll look into how to make sure that our code is actually safe for multi-threading so that we don't go into these situations where we have race conditions and deadlocks. So basically doing unit testing so that our code is thread safe before it gets into bugs in the user's hands. So there are many ways to use QThread, and we're going to look through them. One of them is to have a busy run. Another one is to have the default run. We'll look into a wrapper solution for the problems that Jan will show you, and a fourth solution, which will be moving some objects between threads. And finally, we'll talk about what happens if you don't actually use QThread. So first thing, using QThread by subclassing it. And in the run method, you are doing some sort of heavy calculation, or you're blocking on a socket or a file. So basically, your thread is doing one thing and only that, and it's not listening for events at all. It never goes to an event loop. This is one valid way to use QThread, but obviously only for that use case. The use case where the thread will be busy and blocking and doing something, and it's basically in its own bubble, it's not listening to the outside. This is fine. You just have to realize that when you do that, you will not be able to have any slots in an object in that thread, which will be called due to a signal emitted in another thread. Because when you do signal emission that goes to a slot, if it's between threads, this actually goes through the event loop. So if you're not in the event loop, you will never see that event, and basically the slot will never get called. This is logical. You just have to realize my thread is either busy doing something, or it's sometimes in the event loop waiting for events to come in. It can be both at the same time. But of course, you could have threads that do a bit of both. They do a calculation, then go back to the event loop, wait for the next slot to be called. Then in that slot, they do some calculation. This is fine, of course. But it's not exactly this use case, because this is really no event loop. Now let's go into the use cases where we do have an event loop. It wasn't the case in the initial 4.0 release, but at some point later on, that virtual run method was changed to actually call exec, to go to the event loop. So that means you can do the kind of thing I was just talking about, where you have a thread that waits for some work to be done, and that work is in slots. And this will happen through single slot invocations from the main thread. Now, the trick when you do that is, where are my slots executed? For any object that is created by this thread, the slots will be executed in the thread. That is fine. That's exactly how it's defined. Now, the trick here is, if you put these slots in the QThread object itself, you have to realize, okay, who created the QThread object? Oh yeah, the main thread, which means the main thread is going to execute your slots. And that's exactly what you don't expect in this kind of code. It's a pitfall that has been covered many times on the internet already, so I'm probably telling you something you know already, but otherwise I want to insist on this. The major pitfall with deriving from QThread is to put slots in that class. You don't want to do that, because they will be executed not in that thread as you would think, but in the main thread. So this is too dangerous, don't do that. So basically, if you want to derive from QThread, it's okay, but no slots. But then, of course, you know that, but your coworker doesn't know that. He will add a slot later on. So it's a bit of a dangerous situation, because you are using something that goes into a direction that might become dangerous later on. So let me show you an example of the code that would look like this. Hold on, I didn't set up that. Right. Let's open this file here. It should come up on one of the screens. Yep, it's behind this. So we have this class which derives from QThread, and let's say we want this thread to wake up every 200 milliseconds and do some work. So we create a timer in the thread. We create the timer here, we connect to it, we call start, and in the slot connected to that timer, we expect to do some work in the thread. Now the problem is when we actually run this example, we'll realize that it doesn't do what it's supposed to do because, as I said, this object, the QThread derived class, is actually created by the main thread, so the slots are executed in the main thread. And you have a first hint here about how to debug these kind of problems. Very simple. Let's put in an assert that says, I want this code to run in my thread, so I will check that the current thread of execution when I'm here is actually this. And of course it will fail in this example because of the pitfall I was mentioning. But at least you realize that by having your assert about your program, so you know that something went wrong, and instead of debugging much later on something weird that happens because you didn't realize this was in the wrong thread. So how can we avoid this problem? A solution I wrote some time ago was, okay, let's not derive from QThread, let's separate the two. We want a QThread that is really just there to wrap a thread of execution, but all our code we're going to put in a separate Q object. So on that Q object we can have slots, that's fine. So the class I wrote is called QtDD12. It's actually a template class, and what it does is to instantiate the, so it creates a thread, but in that thread, in the run method, it will create our object. And this way we obey by the rule that we want the object to be created by the thread so that the slots execute in that thread, right? Now, this becomes a bit tricky because we are going to create the object inside of run, but we might want to connect to it from the outside, and obviously that means it does not exist yet. At some point it will be created by the secondary thread. So that needs a bit more synchronization. There is a semaphore in there to actually wait for the object to be created before we can actually use it. So if we look at that, there we are, not this one. Okay, let's go to QThread runner. Oh, it's not here actually. I didn't port it to Qt5. Right. Right, that's the one. So now we will simply change the code from the last time. Instead of deriving from QThread, we derive from QObject. And I call this the implementation of my thread, so I call it thread impl here. Doesn't matter. And this time the slot will be executed in the right thread. How do I actually do that? The main this time will say, hold on, where is the main? Down here. Let's create a thread runner that will be able to, create an instance of my thread impl. And what I'm going to do this time is to call start thread. And if we look at the thread runner stuff, what it does in here is, after much documentation, the start thread method basically calls start, the one from QThread. So at some point, a secondary thread of execution will be created. It will go into run here, and this is where my object class will be instantiated when we do new T here. And we want to synchronize with that. This is why we have the semaphore to actually wait for this to happen before we return from start thread. This way we can actually return the value here, the object that we created. We can return it to the caller and he can connect to it. So all of this is a way to use QThread. We don't actually derive from it in our main code. We hide that in this template, and in the main code we simply we have our object and the slots are running in the proper thread. So that solves the problem, it makes it work correctly. But all of this is a little bit cumbersome, so actually what happened recently is that the documentation was changed so that another way is provided. It doesn't really remove the need for this one, it's a bit of a different way of doing things. I need to find my presentation again. Where is it? Interesting. There it is. So another way of doing this is, we said we want to separate the thread and the worker object. Qt actually provides another way of doing that. which is we'll create the thread ourselves without subclassing, so just new QThread. We'll create our own worker object with the slots and everything. And what we'll do then is to move the worker to the thread. So we are telling Qt, from now on, I want the event handling for this object to happen in this secondary thread. And when doing that, everything will work as planned. So this is something that is now documented in Qt, in Qt5, but actually it's been backported to Qt4 because no code change was necessary. This is only a documentation change. So you can already apply it to your programs, and it would look something like this. We have, again, some implementation that derives from QObject, and the slot will be executed in a secondary thread. The way to make sure of that is here. We create our own object. We also create the QThread, right? We create the two things. And then what we are going to do is, the important line is here, we are going to move the object to the thread. That's the moveToThread call here. Now what gets a bit tricky here is the initialization and deletion of these things. If I needed to do some initialization, I can't really put it in the constructor of the object here because that is running in the main thread, and I might want that initialization to be in a secondary thread. So instead of putting that code in the constructor, what I have to do now is to put it in some slot. Let's say we call it doStart, and this one will be called when the thread starts. So later on, not now yet, but only after the start that is here. So we'll go here, the secondary thread will start, and it will emit started, and at that point we have moved the event handling for impl to the secondary thread, so doStart will actually be called in the thread. Right? That's what we wanted. We want to do the initialization in the secondary thread. Same problem for when we are done. When do we actually delete our own implementation object? Well, when the thread is finished, there is also a signal for that, and we can simply connect that signal to the delete later of the implementation. Any questions? Yeah, Jens.
Same to create and access UI elements others than the main thread.
You cannot do any, you can't create any widgets, for instance, in a secondary thread. That's one of the basic rules in multi-threading in Qt. The main thread is called a GUI thread. Anything that uses widgets or pixmaps has to be done in that thread. I suppose it's the same for Qt Quick as well. So in secondary threads, what you want to do is computations, any kind of, like networking or these things, and then they use signals and slots to communicate with the main thread to display results or show progress or whatever. Yes?
I'm a bit confused. I think the thread object lives in the main thread, right?
Exactly.
And if you move the thread to that thread object, it's still in the main thread, right?
If you move to thread on the thread object itself, and that is a piece of advice that people have given on the internet before, and the Qt developers have reacted very strongly against that, because QThread is really not a thread. QThread is the management of a secondary thread of execution. And that management is supposed to happen in the main thread, or in general, in the caller thread. So if you move to thread the QThread object itself, you could basically confuse Qt. You're saying that code that you expected to happen in the main thread, now let's put it in a secondary thread. The management of yourself, it becomes really weird. And it happens that it seems to work for some use cases, but it's really not a good practice.
I mean something different. I mean, move the thread to some object means that we move the object in the context of that object, right? And the context of this thread object is the main thread, because that's where the thread lives.
No, you're confusing two things, I think, or maybe I don't understand. Okay, so let me step back. Maybe I'm going a little bit too fast. I tend to do that. The way this works in Qt is anytime you create a QObject, that QObject is associated to a thread. And when we say associated, it means the event handling for this object happens in that thread, right? by default, the thread associated with an object is the one that created this object, which is why initially the associated thread for these two things is the main thread. When we go to that line here, we say, please move the handling of the events for impl to that thread, not to the thread associated with that object. We say to that thread. This method here takes a QThread pointer. You wouldn't be able to give any other Q object here which is not a QThread. Okay, so that's where the confusion came from. Yeah.
Would it be valid to initialize thread impl with some plain data before I move it to the thread? Is there anything against that?
Sure, you can. There is a constructor for this thread imp for your worker object. You can of course initialize it with whatever you want. You should initialize it to avoid using uninitialized data. The only reason why you might want a do start thing is if you start to actually do some work in that object, like connect to a server or whatever. Anything that you create in there. Actually, that's a good example. What about the child objects? Do we have? Yeah, the timer here will not move to the secondary thread. So that's exactly the problem here. It will move. Okay, so when you move an object, all the child objects move with it, and that's why this works. Good point, thanks, Tiago. But still, there are some initializations that you might want to only do in the thread and not in the main thread, maybe because they are blocking, like you do a database query or something, and in that case, you might want to move that to the do start method. But of course, if you don't need that, you don't have to do it.
But below you create the button with the parent which is moved to another thread. Where's this button now?
I'm confusing you by having a parameter here, but this is not the parent. The parent is 0. Okay. I didn't show that code. This is really just the test code in the GUI. We create a push button. That button will simply allow us to quit the thread. And I create this button with a 0 parent because that's my top level. And when you click on it, I want to call this method, and this is a good opportunity for showing you how to actually quit that thread now. We don't actually need to keep a pointer to the thread itself because we can get it from the QObject. It's the associated thread for that QObject. And when we call quit on it, we are basically posting an event to its event loop to say, please quit. So obviously it won't happen right now, it will happen later on. So in the old way of doing things, you might be used to, when you were deriving from QThread and you were simply having some code in run, you might be used to simply say quit and then wait. This was the standard way of doing it because quit is simply posting an event. You don't know when it will be handled. You might want to wait until you, for instance, delete the thread. That was the typical idiom for doing that. But in this example, if you remember correctly, I've connected the finished signal to the delete later of the thread. So if I do this, by the time we get here, the thread might actually be deleted already. So you have to choose, it's one or the other. Either you do the delete later solution and the thread just goes away by itself when it's done, or you remove that delete later line, and instead of that you do quit, wait, and delete. Then you actually do the deletion yourself at the time when everything is done. Any other questions?
Can you scroll down?
Yes, I can scroll down. Any other question?
So you're calling delete later on the implementation, but not on the thread.
Yep, I forgot to delete the thread somewhere in there. How would you do it?
By calling thread wait, or by calling wait on the thread and then delete. But of course, you need to keep the pointer in your slots there because you cannot access an imp anymore.
Right, we could do that. We would need both pointers in the button here, so that when wait returns, we can so that we can call wait on the thread and then delete it.
Also connect to delete later.
That's what I was thinking. The other way of doing it would be to simply connect thread finish to thread delete later, but isn't that something that got fixed only for Qt5?
Qt
I think I'm looking at Chago. He says yes.
It's fixed on QtDD too. And
in Faure 8 as well,
yes.
yeah. So don't do this with older versions of Qt, because this gets into a little bit of the corner case.
But even the previous one that connects the delete later of the implementation, there was the exact same problem.
Yes, same problem. Yes.
What if some funny code throws an exception which is not? What if an exception is thrown? Will your delete later still be called?
Okay, two things. I can see from the question, well, I know you don't do much Qt development. We don't use much exceptions inside of Qt, right? So that's why you see many things in Qt which are not really made for exceptions.
The finished signal is emitted even if the thread has had an exception thrown, because it comes from the thread cleanup blocks. So when the thread exits, it will emit the finished signal even if it was because of an exception.
Thanks, Diego. Yeah, good. But we are very careful with the exceptions, because if they go up to the event loop, then Qt doesn't really know what to do with it, and you're under this problem of basically an uncaught exception. That's almost the case here. If you can think of the run method of QThread as being the main of that thread, right? It's really just like main, but inside of a separate thread. And throwing exceptions out of that it sounds to me like throwing exceptions out of main, which is something you don't want to do, right? That's what I meant. But yeah, you could do it, but in terms of what should happen, it's always. But it's good to know that Qt handles it. I just wouldn't recommend doing that. Okay, just let's open a parenthesis here. We all love Qt, but what if we are in a situation where we end up with another framework, let's say Corba or the IBM Rhapsody stuff or Boost? All of these things, what they do is they create their own threads. So they are not Qt threads, they are really native threads created by some other framework. What happens in Qt then? Will Qt be able to handle events posted to QObjects in these threads? I ask the question to you guys. Do you think it will work? Raise your hand if you think it will work. Of course, if you raise your hand, everyone's going to raise their hands. Okay, so as confirmed by the Qt developers here, yes, it will work. Now, how does it work? It works because Qt internally will create a QThread object for you as a sort of a wrapper around the actual object. What was it? Non-QThread. Let's have a simple example here where we use pthread create. So this is Unix specific. I can make the font larger. Very good idea, Thomas. Large enough? Yeah, good. And now it doesn't fit anymore. Thank you. I can maximize. This crowd has lots of good ideas. Very good. So let's have an application where we create a thread by hand using ugly pthread API, so that we don't use QThread. Okay, so at this point here, we create a secondary thread which runs up there in thread start. And because I am curious, what I'm going to do there is create a QObject and ask it for its associated thread. And what you see when you do that is a different pointer value than the one you had initially. And the class name is QThread, so well, it has to be, right? This method returns a QThread. And so it shows that Qt has actually created a thread internally. Now, if you think about that, this is exactly the same thing that happens at the beginning of main. When I do app.thread here, and I ask for what is the associated thread for the application, you also get a pointer to a QThread that you didn't create yourself, but Qt took care of that for you. What this means is that you can use that thread method that asks for the associated thread for any object. It will work in all cases, in the main thread, in a QThread that you created, or in some other native thread. Okay. And there is a second part to that. sometimes as a consultant, you talk to customers and they have weird use cases in mind that the Qt developers never thought of. And their use case was, what if I put all of Qt in a secondary thread, including the GUI? Can I create widgets there then? I don't want to use any Qt in my main thread, it does all the things, I want to move all of Qt into a secondary thread. And of course the Qt developers are like, no, it's supposed to be in the main thread. Actually it's not, right? What we call the main thread in Qt is the thread where Qt application was created. It doesn't have to be the very first thread that was, it doesn't have to be in main. So, I didn't do the hand raising this time, but you get the point. Yes, this will work if the main thread does not use Qt at all, but really not at all. Let's have an example. QThread. Yes, I will make the font larger. And so we have some GUI, doesn't really matter, that's really just for testing. What we are doing here is we have a main. In the main we create a secondary thread by hand again because we don't want to use Qt there. The customer was already having their own code, it creates a thread, and in that thread what they want to do is use Qt. So obviously at that point they need to invent a fake argc and argv. They don't have it anymore, they don't actually matter for this. So let's just create something empty, and we'll create a Qt application instance. So there we are, we do the X11 initialization if we are on Linux. And then we create widgets and everything, and this actually works. The funny thing is, it breaks as soon as you use any bit of Qt in the main thread. So even a simple QDebug like I had here would create a warning that said the application is not being created in the main thread, basically. Because the very first thing that Qt would see would be in some thread, and then the Qt application creation would be in another thread, so obviously this broke. So at the time I thought I was clever, I looked into the source code of Qt, and I found some internal function that could tell Qt, this is now the main thread. There is this weird Q internal call function set current thread to main thread to force Qt into thinking this is now the main thread. And Thiago is laughing because he never thought anyone would find this from the outside. But of course, the joke is on me because this is actually gone in Qt 5, so you can't actually do that anymore.
Careful at global constructor. If you have global objects.
Yes, global objects could be a case where you have Qt code running in the actual main thread, and then this would break this whole idea.
You know why this is gone? Because that was created for Jambi. If you remember Jambi,
yeah.
Java uses a lot of threads, so it created all of this Q internal stuff for Jambi. And then we thought, no, nobody's using Jambi anymore in Qt 5. We can remove the function.
Yeah, I saw that in the commit log. I thought it was removed because Jambi didn't matter anymore. And I thought, come on. Well, I'm a consultant. I give the answer to the customer at the time. I don't really care anymore. I don't know if they're actually doing that. It was just an idea. Okay, so this was actually a long parenthesis on how to use QThread, but this talk is supposed to be about debugging, and we haven't done any debugging yet, apart from adding a few cells. Right, so let's have a look at what's a race condition and how to detect them. So I'll show you a small example. Race condition, hold on, it's not actually here. Yeah, this here, as soon as I move this away. I guess most of you are familiar with the idea of a race condition. I have two threads, they both call this code, they are both running this at the same time, and all that happens there is incrementing some integer. So what the two threads are going to do at the same time is read, and then modify, and then write, and obviously there is no protection here, so the big risk is that they both read some old value, they both increment the same old value, and then they both write it back. If you only do that with about 10 times, then you might not actually see the problem very often, but if you go to bigger numbers, then you actually never reach. I tried with 100,000, you would never ever get near 100,000, you would only get to 200, 300 if you're lucky. So there is a real race condition there, and the good thing with that example is that it's actually easy to see because it doesn't actually go to that number. But the problem very often is that you don't have an actual way of detecting this on every run. It's something that happens not that often. So the question is, how do we detect that? There are three ways of detecting race conditions. The first way is to read the code, but you have to be an expert to actually detect all the race conditions when doing that. The second way of doing it is because you have some results that are very frequently unreliable. That's when you're lucky. And what happens if you're neither expert nor lucky? You want a tool. You want a tool that will tell you this is what the race condition is. And that is exactly what Helgrind does. So what's Helgrind? It's, you know valgrind on Linux especially and Mac nowadays. Valgrind is a processor emulator. It can detect many kinds of problems. You know it mostly for memory checking. But it can also do, with this special tool that it has called Helgrind, it can detect race conditions. So let's have a look at what happens when we do that. Hold on, not there yet. I need a terminal, which is on the wrong screen. Something has to be done about OpenOffice and presentations. I need to bring this there and bring this back. Yeah, there we are. Right, so our race condition example is supposed to count until 20 because we have 2 threads going up to 10. And if I run it many times, it says 20 all the time, so everything seems good. Now, instead of doing what I just did and running it by hand multiple times, we can actually use the shell for this. We can use the repeat command, and we can ask repeat 50 times this, and at some point in there, instead of 20, I got 14. So there is a bug in there, and you see it doesn't happen that often, but you've just learned one way of doing this. With a repeat command, you can actually increase your chances of actually seeing the bug, provided that this is a unit test, something that can be easily reproduced. Now, what we can do is to ask Helgrind what it sees in there. And because this is a presentation and I'm lucky, it actually found it the first time. That is rare. Okay. It actually tells me there is a data race between the reading of something of size 4, it was an int. It tells me exactly the file and the line. If you trust me, there is the line here, where this happened. And it says this read is conflicting with a write, which is basically at the same position, same size, so it's the same variable. And when I see, as often the case in valgrind, you need to read 2 back traces to understand what's happening, and when you read both of them, you see this read is conflicting with this write, so obviously some synchronization is missing between the two things. So that tool is quite powerful for detecting race conditions. Of course, for this to work, you have to use Linux. If you use Windows, you have 2 choices. You can buy some tool that would do this. I don't know the names. You would have to find it for yourself. Or you could compile your code on Linux, which is a good idea anyway, to benefit from a different compiler, which will have different warnings and errors, to benefit from valgrind for the memory checking, and to benefit from Helgrind for the race detection. Even if your customers don't care about Linux, you have a good reason to care and to actually make your code work on Linux just for the tools, because they are really, really good. Right.
I have a question.
Yes, good. Ah, good. This way I can play with that.
Is it that with Helgrind you have to match this race condition? So you must have the situation exactly, or?
Very good question. You saw that when I was running the program, I only hit the bug once every 50 tries. In Helgrind, I hit it on the first try, and that is no coincidence. I was a little bit surprised because it might not happen every time, but the chances are much higher. And the reason for that is, so I didn't write Helgrind, right? So I can't tell you exactly how it works. But from what I understand, it looks at the read operation, it looks at the write operation that will happen later on, but when it looks back, it realized there was no synchronization between the two, so there is a potential race condition. That's why it says there could be a race condition here, because if there is no synchronization in between, then it can see that something wrong happened, even if the actual order of operation was correct. So in a normal run, we would have seen 20 because the threads were interleaved. One of them did fetch plus 1 store, the other one did fetch plus 1 store. We didn't actually get a wrong result, but Helgrind saw, oh wait, there is no synchronization here, this is wrong. And that's why it's good. It increases your chances of actually finding the bug. But this being said, it doesn't always find the race conditions, and I'll actually show an example of that. So this is the idea of the perfect world. We have Helgrind, it detects all the bugs in our code, perfect. Well, not exactly. I wish it was that way, but Helgrind isn't actually perfect yet, especially for QtCode, because one of the issues we hit with QtCode is the lock order detection problem. You know the famous problem where you have two threads and one of them locks mutex A and mutex B, the other thread locks mutex B and mutex A. If they both lock their first mutex, they wait for each other forever. There is a detection for that in Helgrind, and here again it will detect, even if you don't actually get a deadlock, it will simply say you have been locking mutexes in the wrong order between these two threads. The problem is Qt is trying to be clever there in Q-ordered mutex locker, and it uses a try lock, and Helgrind doesn't really care. It sees that just as a normal lock, so it actually raises a problem when there isn't actually a problem. So I won't go further into the details, we won't have time for that, but you can go to KDE 243232 and you'll have more information. And I'm still talking to the Helgrind developers about it, and actually they told me how to make the patch that I would like to make in Helgrind, so I'm going to finish that, and hopefully this problem will go away, if they agree with the result. Another thing is glib has its own issues, and it's used by default for the event loop in Qt. So basically, what I want to tell you here is, if you want to use Helgrind today, this is the shell alias that you should set. You should use qt.glib equals 1 to disable glib in Qt, unless of course you need it in your code, but it's probably not the case. And then you start valgrind with tool Helgrind, obviously, and you disable the tracking of lock orders, because you know that Qt will be very noisy, Helgrind will be very noisy about that. And this is not what you're here for. You're here for race conditions. So you just disable that stuff. It is not the most common problem. The race conditions are much more common and much harder to trace. Hopefully we can remove this later on, but for now we'll have to do with it. So Helgrind is not perfect, okay, but we have ways to make it. But it's also a problem the other way around. Qt itself is not really perfect for Helgrind yet. Let's see what the problems are. One of them is inside of Qt there is some code which is called qflag location. It remembers the line that made a connect statement, so that if this connect statement goes wrong, it can tell you your connect statement is wrong at this line in this file. But obviously you can call QObject connect from multiple threads at the same time, and this stuff here is not protected against that. Thiago made an attempt at making it so. It wasn't portable, so he had to revert it. So the solution that I'm using right now is to simply apply this patch, which I extracted from Thiago's commit. I only kept the GCC Linux specific part of it, I don't need the rest. And this is the workaround for this problem right now. It's not perfect having to patch Qt, but it gets the problem out of the way, and we can keep working on what we actually want to do. Any plans for a better solution? We'll have to see. C++11 is a good solution, but that's for some time ahead. Another problem in Qt is that the execution of the event loop races with the quit or exit of the event loop, so this has to be fixed. I will come back to that issue after this conference, and I guess porting it to an atomic data type should actually get rid of the issue. But I'm telling you so that you realize, if you're using Helgrind now and you see some warnings in there, you know that this is not your fault. It's Qt using booleans without checking them. And QFuture itself, which I'll talk a bit more later, also has a race. I've actually submitted a patch for that. It's being rejected. I'll have to do it differently with atomics. At some point it will get fixed. And finally, the last problem is that the atomic classes in Qt5 are seen as racy by Helgrind because they use different solutions on different platforms. On the x86 platform, it knows it can basically just go ahead and read ints directly, which of course Helgrind sees as a race. So the only solution there is to actually use some macros that come with Helgrind to mark the code as, no, trust me, this is okay. And then Helgrind will not say anything about it. So I'm working on that patch. I'm waiting for some feedback from the Helgrind developers because I'm, of course, hitting some bugs in Helgrind as well. And at some point, it will make it possible to actually, but you can already use this patch for Qt, not for Helgrind, so that the markup is added so that Helgrind doesn't say anything about the atomics. Right, so we have done all our patching. We are ready to use Helgrind. Let's have a look at one example where we do that. Someone asked me to review some code for KDE, and the code looked exactly like that. What's wrong with this code? So we have a class. In that class, we have two members, a mutex and a regexp, and we use a read locker on the mutex to obviously protect what we're doing here, and then we call exact match on the regexp. We have a lock, right? Everything should be fine. Yeah, any idea?
Make a local copy of the result first before returning.
A local copy of the result?
Of the boolean, yeah.
Oh, the boolean is fine. It's a local variable, so we get that the string is fine as well. The problem is the regexp here.
Is the exact match a const function?
It is const, right? Yeah, it is const because
it's commutable because they're compiled.
Exactly. The problem is QRegexp will compile the regexp internally on first use, and what happens here is that what this code is telling me, the fact that there is a read locker tells me that it's actually used from multiple threads, otherwise there wouldn't be no problem. But the QRegexp itself is not meant to be used this way. Because it uses a cache internally of the compiled regexp, it doesn't want you to do that. If you look at the documentation, okay, so I'm skipping to the end, I'll go up after that. If you look at the documentation in Qt, it makes a difference between reentrant and thread safe. What this means in Qt is a method is reentrant if you can call it from multiple threads on different instances of the object. And that's not what we're doing here. Reentrant really means there is no static thing inside, so it's okay to use the same method from multiple threads in different instances. But by default, that's not the case. It would require mutexes everywhere internally. Whereas if you see thread safe in the Qt documentation, that means it is thread safe to use this method from multiple threads, even on the same instance of the object. This is quite rare. You will find this in, for instance, QApplication post event. It's okay to post events from multiple threads using the same QApplication instance, no problem. Now, the funny thing about this example is, so I might not have the time to run it. Hold on. So what happens is you run this code, you have very unreliable results. You're supposed to see always the same thing, and it really, this is a good example because it's not 1 times out of 40. It's really 1 times it's right, and 2 times it's wrong. So you can really see that something is wrong. But all you see when you run this, and if you hadn't done the analysis before, is okay, I have unreliable results. Probably there is some memory corruption somewhere. I'm going to use memcheck, right? The default valgrind tool that checks for memory. But if you do that, memcheck will tell you clean, no problem. So you are in a case where you have unreliable results, but no memory problem. Of course, you go to the next step and you think, oh, this might be due to threads. And then you have to run Helgrind. Now, the funny thing is in this case, Helgrind says clean, no problem. Let me actually show you the full code for that, and QReg Express in the other one. Hold on. Yeah. We have 2 threads. They both use the same regexp, which is here, and we get the result from the 2 threads. and then we simply print these results. And for fun, we also call the same method here from the main thread. So basically, we are supposed to see true, 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 right? All of these do the exact same check in 3 different threads. We're supposed to see 3 times true. And in practice, we see false, false, true, and then true, true, false, and all sorts of weird crap. And so now you know why, but what I want to point out is that in this case, most of the Helgrind runs you would do actually don't find anything. And of course that's a bit annoying because it means you can't really find anything. You see that the results are very different every time. False, false, true, true, and so on. Obviously something's wrong. And if I run Helgrind on it, I don't know what's going to happen. Slowness for sure, it's an emulator, but you see no problem and then true, true, true. So obviously it didn't actually detect the problem. And one of the ways to actually get more chances of hitting the problem is to simply run this in a loop. Either you make the loop in your code or you simply repeat 10 times Helgrind, and at some point you'll get to the problem. Hopefully. Well, you know, it is with demos. I did happen to actually get to it at some point. Ah, there it is. So you see how it is with threads. Sometimes you get the problem, sometimes not. But the one time you actually see the problem, you can debug it. And oh yes, of course there is a compilation in there, so I can't do that. Okay. So this one is easy. How do you debug deadlocks? Your application just blocks. You expect it could be a deadlock. You just attach GDB to it. You type thread, apply all backtrace. You get a backtrace for every thread done. So nothing difficult here. I won't spend more time on it. And the last thing I want to talk about is how are you going to make your code thread safe? The best way to do that is to actually write a unit test, and in that unit test you can use QtConcurrent run to call other methods of the unit test in different threads. For instance, I saw some problems with QURL in multiple threads, so what I did was to add some code to the QURL unit test, and what I did there was to simply use QtConcurrent run. I'll show you that quickly. Now it's in the other one, of course. I can write. Yep, of course that doesn't run, wrong environment. Right. So this is a technique that I recommend for doing multi-threaded unit tests. You simply, you're going to use QtConcurrent to run a given method here, the threading helper up there, in multiple threads. Obviously you want this to run in parallel, so don't forget to configure your thread pool to actually have multiple threads at the same time. Otherwise on a single processor machine you would have only one at a time. That won't work. And so basically I ask for 100 threads and I make them run these things in parallel, and in there I use some QURL API which happens to be racy in Qt4 and which is fixed for Qt5. And by doing this here I can easily increase the number if I need to. As you saw, it helps with Helgrind detection, and we also have a thread for a test for the future to make sure that it never regresses. Right? If you make test code, make it a unit test. This way it's not lost. Now the problem with this is, in practice, it didn't hit Helgrind very often. The reason is the implementation of the method up there, what runs in a thread, is really short. So most of the time what happened was that this is like a runnable. The runnable would finish very fast, so the threads would be reused, and I didn't actually get a race, or not as often as I wanted. So what I did to solve the problem was to simply add a little slip here inside of the method, so that the threads would be busy and QtConcurrent would be forced to create new threads. So we would end up with actually 100 threads instead of 5 threads being reused all the time. So this increased the parallelization, and it made it a lot easier to actually see the problem in Helgrind. Right, that's about it. I think that's all we wanted to say. One of the, oops, wrong screen. The initial problem was detected by malloc check, where glibc can tell you you're doing some wrong memory usage, but of course Helgrind can actually do the same. So this is what we talked about, and yeah. So the conclusion of this talk is be careful when you subclass QThread. Probably don't even use it, don't do that anymore. Make sure you test your library code with Qt concurrent. Use Helgrind. For this you might have to compile on Linux. And there is a lot of work to make Qt Helgrind clean, so if you see problems in Qt when you run Helgrind, do report them, and possibly with a patch as well. Okay, thank you for listening, and if you have any questions. Yeah. He's running the other way, I'm sorry.
I actually didn't get why the irregular expression was erased since you protected it with the mutex. Is it not? So what was the actual problem behind that? I didn't get your explanation.
Yeah, there is a mutex, but a read locker was being used. So it was possible to do multiple calls to that one method because they were considered readers, even though internally it actually writes to the internal state. But the read locker was the problem. With a proper mutex locker, there would be no problem.
If I want to quit my application and have multiple threads still running, maybe even some with a busy run, what's the proper way to do this? I mean, some colleagues of mine say, okay, I just quit, the operating system will clean up after me. It's not quite my philosophy.
No, because of course the program could be leaving temporary files around and you might not disconnect properly, so yes, you don't want to do that. To properly finish threads, you want to do what I was showing with quit and wait, to make sure that you ask them to quit and then you wait for them to quit and then you actually quit. If you look into the documentation, it will tell you there is also this terminate method which can force a thread to quit, and this is also something you shouldn't do because it will do same problems, leave temporary files around, leave mutexes locked for the other threads. So never kill a thread from the outside, always ask it to finish. If it's busy doing something, then you might have to wait for that to happen, or you might to add your own way of cancelling it. Like if it's doing some computation in a loop, you might want to add some atomic in there to actually tell it please stop at some point, even if you don't go back to the event loop.
There's one missing piece. We had one API call that had no timeout. So it was like waiting for something, and it could wait forever. And there was no way we could tell it to stop now, waiting for it.
The solution is to use another API.
Okay.
I'm not kidding. It's easy on the solution. You want to do something asynchronous, or at least something with a timeout.
About the body that runs in the unit test thread, wouldn't it make sense to have a loop there? Because even if you add a delay there, basically many of the threads will just sit around doing nothing. And what you actually want, you want to have a big overlap of many different interleavings of the threads. So probably it makes more sense to have maybe even less threads, but more loops in every thread?
Yes, in general, yes. In this case, what happens inside of QURL is on-demand initialization. So doing the same thing 20 times in the same thread would not give me anything, because what matters is the first run.
I see.
The other runs would basically have nothing else to do. But yes, I agree. In general, you would actually loop over what you want to do just to increase the chances. But the sleep is okay. The fact that I have lots of threads waiting is on purpose, so that QThread pool is forced to create new threads. And even if that happens later in time, this still gives more chances for Helgrind to say, oh, this is not synchronized, what we talked about before. It doesn't have to happen at the same time, it can happen later on, but what I want is that it happens in different threads, otherwise Helgrind will not see anything.
So what you're saying is the problem is not actually happening, but Helgrind has then a way of detecting it, right?
Yes, exactly. What we want with Helgrind is not necessarily to trigger the race and actually get a wrong result, but just increase the chances that two things will happen in different threads, one after the other, no synchronization in between, so Helgrind will say, no, this is wrong.
Are there any other questions? We have still 5 minutes.
Do we? Okay.
I think so, yeah, up to half.
Thank you. I still need some clarification about this connect, the direct connect between difference between direct and queued. Is there a rule now that says when I connect between my main thread and another thread that it will be automatically queued or direct, or what's the rules there?
The way it works is at the time you do your connect, if you don't specify anything in terms of, do you want queued or direct connection, it's auto connection. And what this means is we're not going to resolve this right now. We leave it as auto, and we'll see when the signal is emitted. If the signal is emitted in a different thread than the receiver, or a different thread than the thread associated with the receiver, then it will be queued. If it's the same thread, then it will be direct. The important thing to realize here, and it took me a while to realize, is that the thread affinity at the time of the connect doesn't really matter. What matters is when will the signal be emitted. That's why it's okay to do these things where you connect objects and then you move to thread. You're basically changing the rules, you're changing the associated thread, but that is fine. The connect is still in auto mode. It will wait for the signal to be emitted, it will decide at that point. And this is different from the very early Qt 4.0 implementation, where the only thing that was happening was comparing the associated thread in the connect segment, and that's all, and that was a big problem.
If there are no other questions, we can first thank our speaker. It was very nice.